All right, today we are diving deep into what has to be one of the most exciting frontiers in clean energy. We're talking about transforming our planet's most abundant resource, yep, seawater, into a powerful, clean fuel.
I mean, think about it for a second. Our planet is 71% water. That's a fact so big it's almost hard to wrap your head around, right? More than two-thirds of our world is covered by oceans. We see it as a source of life, weather, wonder, but what if it could be something more?
And that's the huge question scientists are tackling right now. Could this vast, massive expanse of water actually hold the key to a zero-emission energy future? It might sound like something out of a sci-fi movie, but the science here is very, very real. And believe me, it is moving forward fast. So to get from all that ocean water to clean energy, we've got a pretty fundamental scientific hurdle to get over. The promise is absolutely enormous, but so is the challenge. And it all comes down to that simple but incredibly powerful water molecule itself. Okay, so here's the goal. We need to perform a kind of molecular surgery on water, H2O. If we can split it, we can release the hydrogen, the H2. And hydrogen is a fantastic energy carrier. Why? Because when you use it as fuel, the only thing it produces is water again. It creates this perfect clean cycle. But here's the problem. Splitting water is actually really, really tough. It takes a ton of energy. And this is where a really cool process called electrocatalysis comes into play. Just think of a catalyst as a kind of chemical matchmaker. Seriously, it's this special material that brings the right molecules together and helps them react way more efficiently, using far, far less energy than they ever would on their own. So let's put it this way. Without a catalyst, splitting water has this really high energy cost. It's something scientists call overpotential. Imagine it's a huge mountain you have to climb. The reaction is super slow and it's just not practical. But with the right catalyst, it's like you get to build a tunnel straight through that mountain. And suddenly, that energy cost just plummets. So designing that perfect catalyst, that's the holy grail of this whole thing. So how in the world do you build a better matchmaker at the atomic level? Well, scientists have developed this really powerful toolkit of strategies to engineer materials that can split water with just incredible efficiency. It really boils down to four main strategies. First, they can engineer the material's shape. Second, they introduce new atoms into its structure. Third, and this one's cool, they create intentional flaws. And fourth, they build smart interfaces by layering different materials. It's almost like having a set of atomic-scale Lego bricks, You're using them to build the absolutely perfect surface for this reaction to happen. Okay, let's break those down really quick. So, engineering the shape, that's all about creating more surface area, which means more places for the reaction to happen. Then there's introducing new atoms, which is also called doping. Think of it like adding a secret ingredient to a recipe to change the material's electronic behavior. Now, creating perfect flaws. I know that sounds a little weird, right? But these tiny imperfections can actually become hotspots of chemical activity. And finally, building smart interfaces just means using the boundary between different materials to speed the whole process up. All right, so theory is one thing, but let's see how these design principles actually look in practice. We're going to take a look at a recent study that put all these ideas to the test and came up with a pretty remarkable new material. So a team of researchers did exactly that. They put those design principles into action. They started with a base material, a nickel molybdenum phosphide, and then they coated it with a mix of other metals. And the whole goal here was to combine strategies. They created one of those smart interfaces between the different layers, and they were also using the unique shapes of the materials to max out the performance. It's just a fantastic example of a synergistic effect, where the whole really does become greater than the sum of its parts. And the results? Well, they were fantastic. Look, the performance of the bare, uncoated material was okay, it was decent, but its energy cost, that overpotential we talked about, it was still pretty high. The new, coated material, however, that was a completely different story. Its energy cost just dropped significantly. The key number you need to know is 101 millivolts. That's the super low energy cost, or overpotential, they needed to drive the reaction at a standard rate. And let me tell you, in the world of electrocatalysis, that number is incredibly low. It's a flashing neon sign that this new material is a highly, highly efficient catalyst for splitting water. So, what made this particular material so special? Well, a quote from the researchers themselves gives us a huge clue.
They found that the base material had a structure made of these tiny little grains, and that is a perfect real-world example of that very first design principle we talked about, engineering the shape. By creating this massive surface area at the nanoscale, they gave the reaction countless places to happen all at once, which totally boosted its efficiency.
Okay, this is an absolutely incredible step forward. But, like any major scientific breakthrough, it's really just one step on a much longer journey. We still have some pretty significant challenges to overcome before we can actually power our world with seawater. I mean, think about it. Real seawater isn't just pure H2O, right? It's this complex, corrosive soup of salts and ions, especially chlorine. So any catalyst we design needs to be tough enough to survive for years in that harsh environment. And on top of that, it needs to be produced cheaply and at a massive scale. Proving something works in a lab is one thing, making it work for the entire planet, that is a whole other challenge. But what this research really shows us is that the tools are in our hands. By understanding and, manipulating materials at the most fundamental level, at the atomic level, we're not just waiting to discover the future of energy, we are actively designing it. With atoms as our building blocks, just imagine what energy future we can design.